video of mine. In this video, we're gonna talk about exoplanets, or we should say extrasolar planets. What does an exoplanet mean, or extrasolar planet mean? Is a planet outside their solar system orbiting another star. Until now, we had discovered 4,516 of them, I guess. It's hard to have count of them. It's higher than 4,000. Get that one, and higher than 4,500, probably. And so I don't know the exact, and I don't know the one I said is just correct right now. So, exoplanets are extrasolar planets, which are outside our solar system, and we suggest that there is around one planet orbiting at least each star in our Milky Way Galaxy, which will get the count to 1 trillion probably in our own galaxy, which 1 to 20% of them are probably the same composition as Earth, the same size, the same mass, which will mean, this doesn't mean they can be habitable. Probably they have another kind of atmosphere, or their atmosphere isn't like the atmosphere of ours, it's too thick or it's too thin to have water vapor in it. And they aren't in the habitable zone usually, so this doesn't mean they can be habitable. What's a habitable zone? A place, it's a belt around the star, or Goldilocks zone, sometimes scientists call it. Goldilocks zone. It's the best place for life. Earth is in the Goldilocks zone of our sun. Mars is somehow in it. There are two other belts. The belt, after, the habitable zone, see this picture for a second. While I go down, come back again. The habitable zone is somewhere the Earth and Mars, not Mars exactly, somehow in the habitable zone are, and the place between the Sun and the habitable zone is too hot to sustain life. It is where Mercury and Venus are, and the place after the habitable zone, where asteroid belt, Jupiter, Venus, Uranus, Neptune, Saturn, Uranus, and Neptune, Kuiper belt, the Oort cloud are, is too cold to sustain life. The Goldilocks zone is the best place for for life. And there are we have a theory that there are around 300 million of these planets orbiting the habitable zone of their star, of just the 1 trillion exoplanets in our own galaxy. So do we have enough time to see them? Do we have enough time to go and find life on them? Nobody knows. There are many parsecs and light years away from us. The closest planet to us, exoplanet to us, is Proxima Centauri, which is 4 light years away. How long will it take us to get there? Around 40 years with a normal rocket, its engine on all the time. It will get there in 4 years. So probably we'll have to go multi-generational, or there are some other ways we don't know of. And this thing goes in the theoretical physics, and I'm not a theoretical physicist. And so, let's continue our thing about exoplanets. Exoplanets are classified many different ways. There are four main classifications of exoplanets. Number one, Neptune-like exoplanets. Okay, Neptune-like exoplanets, as their name says, they're like Neptunes. They're gas giants, and they orbit the star like in a normal way. But hot Jupiters, classified the second, is Jupiters, like they're same size as Jupiters, probably a little bit bigger or a little bit smaller, or probably many times bigger. They orbit their stars so closely that they break the laws of physics. They're so hot. It probably isn't like that. When a planet forms in a protostar's disk, they actually, there are gas around the protostar before it's born. The protostar is born. So they can collect a little bit of gas around them. And when the sun is born, it sends a radiation and a solar wind which will push all the extra gases and dusts into out part of the solar system. And these parts, when our sun was born, had formed the Kuiper belt for us. But those solar winds had also destroyed the atmosphere of the inner planets because they were so strong when they came out of their sun. They wash the atmosphere of the planets, the inner planets, and get them into the outer solar system. That's why planets in the inner solar system don't have atmosphere, or if they do, like Venus, Earth, and Mars, really thin. Of course Venus's atmosphere is sick for us, but according to its mass, it's nothing, in relative to its mass. But the outer planets, which were farther away from the sun, the solar winds wasn't powerful enough to wash their atmosphere, which means they had turned into gas giants. So, as the laws of nature says, as the laws of physics says, a gas giant should form outside the solar system, in the outer solar system. How come these hot Jupiters orbit the star in the inner solar system? These are mysteries we need to find out. So I'm gonna come back again soon. The third in the classification of exoplanets is SuperEarths. SuperEarths are SuperEarths. Okay, so what are SuperEarths? They are planets, rocky planets, probably rocky planets, a little bit more massive, a little bit more bigger than the Earth, which some of them might probably support life, some of them might probably support deadness and freezeness and meltiness. Okay, I'm not kidding here, I'm serious here, because on some planets, super-Earth planets, the temperature is so high you can melt and become a part of the atmosphere or the lava on the planet. And on some planets, it's so cold, you might probably turn into the ice of the planet. Not you, probably me, I don't know, whoever, okay? So, these are planets with super-Earths which are outside the habitable zone, but a super-Earth inside the habitable zone is the best planet to support life. Trust me. But before you get there, 1,000 years has passed and you have to have a multi-generational trip, and you may never see the planet yourself. Sorry about that. Anyway, so as I was saying, the last in this classification is Earth's analog, which are the same composition as Earth, the same size as Earth, the same mass as Earth. All of their things is like the Earth, but some of them are still too hot and some of them are still too cold. So probably you might have a visit of them in the habitable zone. Those in the habitable zone, you might have to visit them, because the others are super hot. Trust me. Okay, so now we had done the classification of these planets. Now, how do we detect them? How do we see them? We actually cannot see their surfaces, okay, or the top of the cloud. We just have hypothetical visions, some of them visualizations, some of them we had seen. And if you want to see this this fictional classification, visualization, you have to go to this site. The site I had put in the description below. You can visit there, and there are like some other data you can find out, which I had put at the end of the video. So basically, yeah, these planets are hard to detect, but there are 5 major ways that we can detect them, and they are, hard. But the most important one is transit. But the most important of them is transits or microlensing, gravitational microlensing. Like gravitational microlensing is like a star is giving out light, lots of light, radiation, yeah. And if it has a planet can curve the structure of space and time, which will mean the light will bend and will come directly into our eye, while it didn't want it to come into our eye. So that's when we know that this star has a planet. Next is transit. How does it work? We look at the star, okay, a star, we have it under a picture, and we see, we have a diagram over here showing us the light of the star. The light of the star. So when the planet passes in front of the star, this diagram goes down, a little bit curves and then comes up again after the planet passes over. So that's where we find out this planet has a star. Anyway, thanks for watching. I hope you enjoyed and learned new things. Next episode will be about strange exoplanets in the universe. Don't forget to look at this description below, because there are lots of data down there, because since I didn't want this video to take too long, I put them in the description below. Thanks for watching. I hope you enjoyed and learned new things. Goodbye.